Namaste to everyone. I welcome you all in my YouTube video channel. Today I will discuss Tensor Analysis Lecture 6, which will include symmetric tensor, skew symmetric tensor and properties of tensors. Now I will discuss about symmetric tensor of rank 2. A tensor Aij is symmetric in the sense that Aij equal to Aji or Aij equal to Aji. This is symmetric in the case of covariant tensor and this is symmetric in the case of contravariant tensor. Now we shall prove that symmetric tensor of rank 2 we get only n into n plus 1 by 2 number of independent components. Let we write tensors of rank 2 in matrix form. We get A11, A12, A1n, A21, A22, A2n, an1, an2, ann. Here number of components equal to n square, as it is n by n matrix. If we write here matrix sign, so this is n by n matrix. Here number of diagonal components equal to number of diagonal components equal to n. Total number of components equal to n square. So number of components other than diagonal components will be n square minus n. N square minus n contains no diagonal components, only non-diagonal components. But among non-diagonal components, due to the property of symmetric tensor, A12 equal to A21, A13 equal to A31 and A1n equal to an1, A21 equal to an2. That is, for these two components we get only one independent components. For these two components we get only one independent component because the components below the diagonal are dependent on the components above the diagonals. So number of independent non-diagonal components equal to n square minus n by 2 half. Now we include the diagonal components. Number of diagonal components is n. So total number of independent component will be n square minus n by 2 number of non-diagonal components plus n number of diagonal components. So we get that total number of components equal to n square, number of diagonal components equal to n, number of non-diagonal components equal to n square minus n, number of independent non-diagonal components equal to n square minus n by 2, including the diagonal components, total number of independent components equal to n square minus n by 2 plus n, this equal to 2 n square minus n plus 2n equal to n square plus n by 2, that is n into n plus 1 by 2. So number of independent components in a symmetric tensor of rank 2 is n into n plus 1 by 2. Now we shall discuss about skew symmetric tensor of rank 2. We also say skew symmetric as anti-symmetric. A tensor of rank 2 is said to be skew symmetric if Aij equal to minus Abi or Aij equal to minus Abi. Now we have to prove that number of independent components in skew symmetric tensor is n into n minus 1 by 2 independent components. Putting j equal to I, we get I equal to minus Aii, implies that 2Aii equal to 0, implies that Aii equal to 0, that is A11 equal to 0, A22 equal to 0 and ANN equal to 0. That means all diagonal components 0. If we arrange all the components in a matrix form, we get 0, A12, A13, A1n, A21, 0, A23, A2n, dot, an1, an2, an3, dot, 0. Here all diagonal components are 0. Also A12 equal to minus A21. Similarly A13 equal to minus A31. A1n equal to minus an1. A21 equal to minus an2. Similarly, we get that this component and this component are dependent with each other. For two components, we get only one independent components. So, components below the diagonals are dependent on the components above the diagonal. Non-diagonal components are n square minus n. Therefore, number of independent non-diagonal components equal to n square minus n by 2. Here, diagonal components are 0, so no necessary to add the number of diagonal components. So, total number of independent components in skew symmetric tensor will be n square minus n by 2 equal to n minus 1 by 2. Now we shall solve a problem. Problem is that so that a second rank covariant tensor be expressed as sum of two tensors, one of which is symmetric and other is skew symmetric. 2. Let Aij be a covariant tensor of rank 2. This may be written as half Aij plus Aji plus half Aij minus Aji. Let this part is Bij and this part is Cij. Bij equal to half Aij plus Aji. By interchanging suffix I and j in both sides, we get Bji equal to half Aji plus Aij. By commutative law, this equal to half Aij plus Aji. This is Bij. Therefore, Bij equal to Bji. So, Bij is a symmetric tensor. Now, Cij equal to half Aij minus Aji. Interchanging suffix I and j in both sides, we get Cji equal to half Aji minus Aij. This equal to minus half Aij minus Aji. This equal to minus Cij. Implies that Cij equal to minus Cji, which shows that Cij is a skew symmetric tensor. Therefore, Aij is the sum of two tensors Bij and Cij, in which Bij is symmetric and Cij is skew symmetric. Hence proved. Now we will discuss about the benefit of using tensor and properties of tensor. In general relativity, the principle of covariance says that physical law must be expressible in a form which is independent of particular space-time coordinates chosen, or in other words, laws of nature remains invariant with respect to any space-time coordinates. That is, any property holds in a coordinate system, then that property must hold in other coordinate systems. Only tensor plays an important role to hold these properties. Only for this, Einstein used tensor as a tool in his general relativity. Now, we shall discuss the properties one by one. Number one property: if a tensor is symmetric in one system, then it is symmetric in all systems. Let we have Aij be a second rank covariant tensor in X system of coordinates. Its corresponding value in X bar system of coordinates be A bar ij. We consider Aij be symmetric, then Aij equal to Aji. According to the tensor law of transformation, A bar ij equal to del x alpha by del x bar I, del x beta by del x bar j, A alpha beta. Since A alpha ij equal to Aji, therefore A alpha beta equal to A beta alpha. So we may write del x alpha by del x bar I, del x beta by del x bar j, A beta alpha. By rearranging, we may get del x beta by del x bar j, del x alpha by del x bar I, A beta alpha. So this will be A bar ji. Therefore, the tensor is symmetric in X bar system of coordinates. A bar ij equal to A bar ji. Next, we will discuss that if a tensor is skew symmetric in a system, then it is skew symmetric in other system of coordinates. Let Aij be a skew symmetric tensor of rank 2, then Aij equal to minus Aji. Corresponding value of Aij in X bar system of coordinates be A bar ij. According to the tensor law of transformation, we write A bar ij equal to del x alpha by del x bar I, del x beta by del x bar j, A alpha beta. As we have seen that Aij equal to minus Aji. Therefore, A alpha beta equal to minus A beta alpha. So we may write this equal to this. That means minus A bar ji. Hence, the tensor is skew symmetric in X bar system of coordinates. X bar system of coordinates means other system of coordinates. So if a tensor is skew symmetric in a system of coordinates, then it is skew symmetric in other system also. Next property is, if a tensor vanishes in one system of coordinates, then it vanishes in other system of coordinates. Number 3. Let Aij be a second rank tensor in X system of coordinates. Let Aij equal to 0. The corresponding value of Aij in X bar system of coordinates is A bar ij. According to the tensor law of transformation, A bar ij equal to del x alpha by del x bar I, del x beta by del x bar j, A alpha beta. Here given that Aij equal to 0, that means A alpha beta equal to 0. So this will be 0. That means this equal to 0. So if Aij equal to 0 in X system of coordinates, then A bar ij is also 0 in x bar system of coordinates. That is, a tensor vanishes in x system of coordinates, then it vanishes in x bar system of coordinates, that means any system of coordinates. Next property is number 4. The tensor obeys the group property, that means transitive property, group property. Sometimes we say that so-called group property. Its name, other name may be transitive property. Let AI be a tensor of rank 1, that it is a contravariant tensor of rank 1 in x system of coordinates. Its corresponding value in x bar system of coordinates be a bar I. Let we consider one more system, that is x double bar system of coordinates. Its corresponding value is a double bar I. We may get transformation from ai to a bar I, and also a bar I to a double bar I. According to the tensor law of transformation, a bar alpha equal to del x bar alpha by del x L A L. Again, from this to this, we may get a double bar I equal to del x double bar I by del x bar alpha a bar alpha, because first transformation was ai to a bar I. In this case, this side bar, this side without bar. Second transformation is a bar I to a double bar I. Left side double bar I, right side single bar. So, putting values of a bar alpha from this equation, we get del x double bar I by del x bar alpha into del x bar alpha by del x L A L. Here alpha is the dummy suffix. So we may write this del x double bar I by del x L A L. This transformation is from x system of coordinates to x double bar system of coordinates. Equation, this we may take 1, we may take this 2, similar to 1, from x system to x bar system of coordinates. Here similar nature we get x system to x double bar system. That is, transitive property holds. This property is known as so-called group property. Hence, we may quote the properties of tensor. Number 1, if a tensor is symmetric in one system, then it is symmetric in every system. Number 2, if a tensor is skew symmetric in one system, then it is skew symmetric in every system. Number 3, if the components of a tensor vanish in one system, then they vanish in every system. Number 4, transformation of tensor form a group, that is always transitive property. Thank you for watching my YouTube video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.